Okay, so let's review a few Hardy-Weinberg problems for your test. Again, the trick to any Hardy-Weinberg problem is remembering how to get to Q. So often that means that you have to solve for Q squared. So when we look at the two equations for Hardy-Weinberg, we know that this equation here is going to set us up for genotype or phenotype frequencies, and this equation here is going to give us our individual allele frequencies. So oftentimes these problems run through Q squared. So if we look at this word problem here, take a moment to read it, it's going to tell you that there's this phenotype vestigial wings that's recessive. In other words, those are the individuals that are the Q square. So it's saying 360 out of 1,000 are this recessive phenotype. A little bit of quick math will tell you that 36 out of 100 is 0.36. So your Q squared in this case is 0.36. To get Q, we take the square root of that number. Square root of 0.36 is 0.6. And if we go back to this allele frequency equation, we know that 1 minus 0.6 is going to equal to P. So P is equal to 0.4. So now we have our two allele frequencies. We can plug these into the problem and solve for anything, really. They're asking you for the homozygous dominant and heterozygous individuals. So again, that's going to come out over here. Your P squared is going to be the homozygous dominance. So that's going to be 0.4 squared. And your heterozygotes are going to be the 2PQ, which in this case is 0.6 times 0.4 times 2. So if we go back to P here, P is going to equal 0.16. 2PQ is going to equal 0.48, but they're asking you in this case for individuals. So you have to take these frequencies and multiply it times towards the entire population, which, if you recall, is 1,000 individuals. So in the case of P squared, 0.16 times 1,000 is going to give you 160 individuals in that category. 0.48 over here for the heterozygotes times 1,000 is going to give you 480 of those individuals. And so that's the answer to that problem. Looking at a second example, we see that the word problem is going to guide you towards attached earlobes being the recessive trait. The problem is saying that there's 25% attached earlobes, which is like saying 0.25. So 0.25 equals Q squared. To get Q, we take the square root of 0.25. So Q is going to equal 0.5. That also means that P equals 0.5, because if you recall over here, they add up to 1. Now, the original problem, what is it actually asking us to answer? So it's saying, again, how many homozygous dominant and heterozygous individuals would you see for these various traits? So again, we plug in using this equation here. P squared would be 0.5 squared. 2PQ would be 2 times 0.5 times 0.5. And when we look at those numbers, you're going to get a frequency of 0.25, frequency of 0.5. But again, it's asking you for the number of individuals. So we have to multiply these frequencies times the population. If you recall, it's 500. So when we multiply that, we get 125 individuals that are homozygous dominant genotypically, and 250 that will be heterozygous genotypically. So again, just to remind you, all of this runs through Q squared. A third problem is shown here, and it's asking you about a phenotype called widow's peak. It's saying that the widow's peak is dominant over the allele for no widow's peak. So no widow's peak is going to be your recessive trait. So I'm going to write no for that. And the number of no's in this case are going to be 1,000 minus 510, because 510 is the dominant phenotype in this population. So that means 490 out of 1,000 are the Q squared. So again, doing some simple math, 49 out of 100 equals Q squared, 0.49 equals Q squared. Again, the trick here is you want to take the square root of this number to actually get your Q, and that number is 0.7, so consequently, P equals 0.3. We have our two allele frequency numbers now. Now we can go back to the original problem and see what they wanted to actually have us solve. And if you look at that, they want to know how many of the possible 3 genotypes are there. So again, we go to this equation and we simply plug in the numbers we have for the individual allele frequencies for P and Q. When we look at that here, we get, let's see, 0.3 squared plus 2.37 plus 0.7 squared. Okay, and then we solve for that. That is going to come out to 0.09 plus 0.42 plus 0.49, which we already knew from the original problem. But again, it's asking you how many individuals of each of the 3. So we need to take these frequencies here and multiply them by the population, which in this case was 1,000. When we do that, we know that there are going to be 90 individuals with the homozygous dominant genotype. There will be 420 with the heterozygous phenotype and 490 individuals with the homozygous recessive phenotype. Again, it's all running through Q squared. Make sure you can differentiate Q squared from Q. Another problem here, we are looking at the trait for blood type for Rh factor. In the problem, it's telling you that Rh factor negative 16%. So another way of saying 16% is 0.16. So 0.16 equals Q squared. Take the square root of that number to get Q. That number is 0.04. So now we have our number that when multiplied by itself would create that. So, and actually now that I'm looking at that, that is not 0.04. That should be 0.4. So your Q equals 0.4. So your P equals 0.6. And then we go back and see what they wanted us to do with this problem. So if the student population in high school is 2,000, how many would you expect to see each of the 3? Okay, so we're going to take P equals 0.6 and Q equals 0.4, plug it into this equation here. When we do that, we get 0.6 squared plus 2.6 times 0.4 plus 0.4 squared. Again, this is going to give you the genotypic frequencies. In order to figure out the individuals, you'd have to multiply it by the entire population. But when we do this, we get 0.36 here plus 0.48 plus 0.16. First time we're seeing a population of 2,000, so we want to make sure that we multiply it by 2,000. When we do that, there are 720 individuals that have the homozygous dominant genotype for Rh factor. If you remember from genetics, that's basically going to be like this. There are 960 actually, 960 of the heterozygotes and there will be 320 individuals in that population of 2,000 that are homozygous recessive. Okay. Considering sickle cell anemia. So looking at the word problem, 4% of newborns have sickle cell anemia, which is a recessive trait. I hope you're appreciating the theme here that all of this runs through the recessive phenotype. So sickle cell anemia equals recessive equals Q squared. And they're saying that there are 4%. Another way of saying 4% is 0.04. Okay, so how do we figure out Q? Well, Q is the square root of that number. And when we do that, we see that Q equals 0.2. So consequently, P equals 0.8. Now we're ready to plug in any of these numbers to figure out any sort of question that they could ask. Let's see what they're actually asking. They're asking in a population of 1,000, how many would you expect for each of the possible 3 genotypes? So it sounds like this is a good idea that you know how to do all 3 genotypes. Again, we go back and we look at this equation. We plug in our numbers, 0.8 squared plus 2.8 times 0.2 plus 0.2 squared. When we do the math, it gives us the following frequencies for each of these individual genotypes: 0.64, 0.32, plus 0.04. When we do the math, which is to say we multiply it times the population, which is 1,000, we see that there are 640 individuals that are homozygous dominant in a population, 320 heterozygotes, and 40 homozygous recessives. Last problem. In a certain population, the dominant phenotype occurs 91% of the time. That means 9% equals recessive. Okay? That means 0.09 equals Q squared. How do we figure out Q? We take the square root of 0.09, which will give us 0.3. Therefore, when we subtract, when we do the math from this equation, we see that P equals 0.7. What is the question actually asking us? Well, it's just asking us the frequency of that dominant allele. So officially that problem is done because we figured out the frequency of the dominant allele represented by P in this particular problem. Okay, I hope that helps. It's going to be good practice for your test.